So we are continuing with our look at the work by Howard, and we have since established the model that we are concerned about or we are concerned with. So yes, we are still looking at our paper, the paper that we have been discussing for some time now, the SIR model and the foundations of public health. Trust me, at the end, at the very end, we are going to apply some machine learning techniques so that we actually have a complete evaluation of how a disease is discussed or is talked about in terms of public health policy. So this is just a foundation so that when we start doing that, everybody will be on board knowing what we are talking about. So we got the model. Let me just write down the model as we had it. We had ds dt is equals to minus beta si. So we are simply saying that if you are in compartment S, all right, this is the compartment for the susceptible, you are going to leave this compartment at a rate beta because this is the rate at which the people that are susceptible, meet the infected, which is Si there, actually get infected. So Si is the interaction of the susceptible and the infected, and that rate of is beta, and at the end of the day, beta Si is the incidence term, all right? And for the number of new infected individuals per unit time. But remember, we assumed that there is homogeneous mixing of the infected and susceptible classes. All right. Now, what happens is that because we are having people that were not sick but now are sick, so they are going to leave the susceptible class. Hence, it is what? It is negative. These people are going to be received somewhere, so we say positive. So they are going to be received in the infected compartment. The IDT is equals to positive BSI, but also some of the infected are going to recover, so we subtract. Nu or V there. A portion of the infected is going to recover. So these are going to the recovered compartment. So we have the last equation being the RDT is simply equal to positive VI, like that. So the total population size should remain constant. And this easily follows from the SIR system. So in other words, if we are going to add the SDT plus the IDT plus the RDT, what happens is that if we add them up, if we add everything up, let's see what happens if we do that. We are going to get that we have got this guy, because this is the SDT, right? So we are going to add him and say minus beta Si plus beta Si minus Vi plus Vi. So the answer is 0. Why? Because if we add this and that, knowing so well that our population N is equals to S, the number of people in the susceptible compartment, the number of people in the infected compartment, the number of people in the recovered compartment, but N is constant because the population is not changing. So if we add the SDT plus the I, dt and also dr dt, what we must expect to get is dn dt. We are expecting to get the rate at which the total population is changing. But we figured out that this will be minus beta si plus beta si minus nu I plus nu I. And we said this will cancel with that, and this will cancel with that, and the answer is equals to 0. In other words, you're saying the rate at which the population is changing with respect to time is 0. So the population is constant. It is not changing. The population is not changing. All right? So while we have got the term removed, according to Howard, and we said removed can mean dead or recovered, it becomes more obvious that we are talking about a recovering population here more than the dead population, because we cannot say the population is not changing while some people are dying. That will not be meaningful at all. So that's what we have. So we go back again and we realize that, okay, so the total population size is not changing. And another thing that and also we can calculate the number of recovered by simply making R the subject of the formula from this equation, because if we make R the subject of the formula, then we get RT, and we say, look, the total population minus the susceptible minus the infected must give us RT. All right, so because R can be written in terms of S and I, and also the fact that N is basically a constant. So the susceptible is changing, the susceptible compartment or population is changing with respect to time. The infected population is also changing with respect to time, but N is not changing with respect to time, to the extent that it might not fairly be correct to actually write NT like that. Just write N because it's a constant, it's not changing with respect to time, okay? And it means that instead of writing R in our system, we might have to include it because R is made up of S and I, then it means that the system can be reduced to a system of two ODEs. The system can be reduced to ordinary equation number 1 and equation number 2, which is this one and that one I've got over here. How? Well, there is something that we could have noticed at some particular point in time. Suppose that each infected individual has K contacts. That is, you conduct about K people, because we assume homogeneity in the mixing. So yes, each individual has K contacts, each sufficient for transmission per unit time, and K is independent of the population size. Then what we then have is Ks over N of these contacts are with susceptible individuals. In other words, we are simply saying, look, a portion K of the susceptible. So this is a portion K of the susceptible divided by N. So it means that of the total population, we have got a portion K of the susceptibles. I think it makes sense. It must make sense to you. So we have got Ks, where K is that each infected individual has got K contacts. All right. So K contacts in the susceptible, then divided by N. So this is the portion of susceptibles of the total population of susceptibles that actually gets into contact with sufficiency for transmission, right? And if the fraction T of adequate contacts results in transmission, then each infected individual infects KTS. Can you see now that these are contacts sufficient for transmission, but the transmission itself, the fraction T of adequate contacts. So we go to the contacts and take a fraction which actually adequate for transmission to take place. Then, in other words, each infected individual infects this much number of people per unit time. It's very, very important to understand that we have got a fraction of a fraction. So we have got a total population, and in the total population, this portion is for susceptibles. And in the susceptibles, we have got K there, that the contacts that we are referring to say these each infected individual has got K contacts. So this is the amount of contacts for an infected individual in the susceptible contacts, in susceptible population. But in this K, we take tau. So this population as well that I take. All right? So we take tau, and we are saying now tau represents adequate contacts that result in transmission. And at the end of the day, each infected individual infects KTSN, because KT here is an interaction of my contacts and adequate contacts that result in transmission, and then S is the susceptible population. So we have got now that we remember we're saying that ds dt is equal to minus beta Si, isn't it? But now we are getting a more precise definition of what beta might be. And we are now finding out that beta is actually equal to KT. As you can see there, beta is actually equal to KT over N, if we are to just exclude the susceptible population there. So the parameter T is called the transmissibility of the infectious disease. How transmissible is the disease? Because certain diseases that are waterborne, it means that their transmissibility might be less compared to diseases that are contagious. I want you to understand, if we are talking about cholera, which we pass to each other because you drink dirty water, which maybe is coming from my house to your house, and then you consume that dirty water, it's different from me meeting you and then passing the disease. There is a higher chance of transmissibility if it is contagious than when it is non-contagious. So I want you to understand of transmissibility from that perspective. So this is the analysis, or at least the description that was given by Howard concerning the model, and I've tried to talk about it in as few words, as many as is possible.